Good night, everyone. I would like to introduce Chris today, a member of PyData TT. He's going to talk about potholes and pandas, basically. So just a quick reminder of the code of conduct. Be kind to others, do not insult or put down others, behave professionally. Remember that harassment is not tolerated. All communication should be appropriate for a professional audience. And PyData TT is a very inclusive environment that does not tolerate harassment. So with that, I'll hand it over to Chris.
Hi guys. So today I'm gonna be sharing a quick short talk. I'm gonna be sharing some experience I had with pandas and some of the things that I learned along the way. Right. So how did this journey all started? Well, as with anything in computer science, it was always about an algorithm. Right. And it looks something like this, a bunch of nested for loops. Right, and you write the code, and the data set that I was using there with about 15,000 rows, it took like literal days to run in some instances, right? So that obviously wasn't gonna work. So I was wondering, well, what's going on? I've been using pandas for a while, so I didn't really think it was the code, and we verified that the algorithm was correct and it was sort of doing what it's supposed to do. It was just slow. So I reached out to our friendly neighbor Torian here, right? And after interacting with him, the algorithm looking something like this, which is vastly different from what we had before. And it even ran in minutes rather than hours and days. And it turned out that I was actually using pandas and not using pandas at the same time. So that was a little bit confusing. So what I'm going to do is here to take you through the couple of things that I've learned, which will show you how to use the Pandas API properly so we can leverage speed. All right. So I thought I was using it, and it's very easy to write slow Pandas code. So hopefully you can learn from my mistakes and avoid these problems. So let me start with a very simple data set. Right. So we have this this is a demand profile here in terms of energy and time, right? And the first thing when you get and you load this data set, you would think that well, this daytime field here, it looks, just like as you would expect it. You would expect it to look like a daytime. But if we check the types for it, right, you'd realize that it actually isn't a daytime, right? It actually is an object, right? Which may or may not matter to you. It kind of depends on what you're doing, right? So when would this really matter? Well, it would matter when you're doing stuff with functions like the toDaytime, right? Because if it's an object, a generic object, and it's not typed, then the Pandas API, it would allow the code to run, but it would spend a lot of time trying to figure out what type it is. And even if it figure out, well, what sort of daytime it is, it need to figure out what is the format and this kind of stuff, right? So that's a lot of computation time that's being wasted when you actually do know that it's a daytime and you do know what the format is, right? So if you were to rewrite that, if you were to write that code, like typically how you do it, like how I've been doing it for a while now, you just simply pass in your data frame column there to the daytime function, and you call convert on that, and that's it. Everybody's good. So this takes about 1.1 seconds, just roughly, right? So that seems okay. The data set that we have here is about 8,000 rows. But then how about if you were to scale this up, right? So this is a energy data set that we get from like one of those companies like TNTech, right? So suppose your resolution increase by a factor of 10, right? So we have 10 times more rows, and it was distributed over 300 different sites or 300 different like counties or something like that. Then just simply converting that simple function that we tend to write all of the time, simply converting that object into a daytime format would take 49 minutes thereabouts, which was kind of mind-blowing to me, right? And this is something that I would write like all the time. So how do you work with that? Well, what was the issue? right? The issue was that the API needed to spend time to figure out how things was organized. So the simple way to get around that is that you can manipulate the format parameter, right? And then if you do that, you remove the guesswork from the API. So the API knows exactly what it is, and it can just focus on the number crunching. So the code will look something like this here, right? So just as we had before, it's just here now we have this format specifier, and I mean look at the performance gain there one time, right? We're going from seconds to milliseconds, right? So yeah, so this same thing now, if you were doing it across 300 sites, you would have gone from 49 minutes to about just roughly 2 minutes. That's a 26 times improvement, 26x improvement, very minimal code. And again, it comes back to the theme of the talk here, is that you may have been using this thing for a while, but you're really not using it to its fullest potential. So our next gotcha that I had, took me a while to figure out, was how to do loops properly, right? So let's just say if the cost for this energy example here that we were working with, things were static, then if you wanted to work out, well, what is the amount of money you have to charge people? Let's say it was 28 cents per kilowatt hour. You do something like this, yeah, this would run fast and it'll be fine, because this pandas actually does something called vectorization. So this is actually vectorized underneath the view, right? And we don't really think about it. But let's just say if your rate was now conditional, so you charge a different amount based on the number of hours that you used. So typically, how you do this, so I would have done it in the past, is you write a little apply function here, right? So you have your conditions, the different ranges, and you adjust your reads accordingly, right? And then of course you just return the rate times time, right? So that seems pretty straightforward. And then what you would do with this, you would have this apply function, and then we just need to apply this to every row. So we just reach for our traditional for loop. So then it will look something like this. For I in the range, we go through, we look up the row, and this index I, extract the time, apply our function, get the data, store it in a list, and then when you finish, take that list now and map it back as a column, right? So again, 8,700 rows, about 2.3 seconds. Seems innocent, but it's really is not when you want to scale, right? And what's the issue here? You might say, well, this seems fine, right? You shouldn't have any problems. The problem here is that we're doing too many things that are not really concerned with the actual computation. We're doing a bunch of lookups, and then we have to manage this list. The list operations in Python. These are not this list here is not like a panda, something from pandas or NumPy or something like this vanilla Python. So those operations would be slow by comparison, and then we have to take that entire list and stop it onto the list. So all of these are things that we're doing that is not really about what we're here for, which is to do the computation. So this is really long. So how do we fix that? So we know these are the issues here. So the first thing is well, let's see if we get rid of trying to pull out these indexes. So pandas has something called iter's rows. Right now, what that does, it yields an index and a row tuple, right? Instead of having to go and look up the value each time, what it would do is it would have a loop, but that'll be in memory and it will store it somewhere. And then anytime you want the next row, it will just pull that function out and continue the execution and return that reference to you, pause it, and then go back, right? So that's how the works. So how the code look, right? So it's very similar to before, but here now we have our index and a row tuple that's returned by this iter rows function, and that's basically all we would have to do for now, right? So we do that, and then for the row we just pull out the columns that we want, and call the apply function. And then we're off to the races. We're still doing the list operation, but just with that alone, just with that changing that one line here, right, and how we access the information, just with that one line, we're down to 1.5 seconds, right, which is pretty good. So that's not too bad, about 4 to 5 times faster. Fine, that's cool. So how do we get rid of the other things? So the other thing that we're dealing with here is this list. Managing this list and then trying to build that and apply it back to the data frame. So the first thing you could reach for is the apply function, right? So how to say, like if you really don't have the time and you just want a really quick speed up, you could reach for the apply, right? But there are many things that you can do that would give you much faster speed and more gains than simply calling an apply function, right? But how does the apply save the time? Well, that handles all of the coordinating logic of taking that function and applying it to each row in the data frame, right? And especially if you have multiple cores, which most machines have, or if you're running a GPU, it will handle all the intricacies of parallelizing that operation, right? So how the code change? Well, apply takes this lambda function, right? So the same apply tire function we had that, we just wrap that inside a lambda function and pass that to the different.apply, and that would run it first. So we gone from 0.5 seconds to 0.1 seconds. So yeah, we get in somewhere. Right, so that's about 200 times faster. And notice here, in this case here, we don't have the for loop, right? We don't have the for loop because the apply handles all of that coordinating logic field, right? So many a times when we're writing stuff for data science, right, we think we need for loops, but we really don't, right? That logic could be handled by these APIs, which would be able to do these things in a much more efficient manner than the other kind. Right, so good. So we get in somewhere 200 times faster. All right. Now, what about if you had to deal with multiple if else? That's another common thing you might come up in your code. All right. So there's something we could use called is in, and again, this builds back to the key idea. What we're doing here is that we take in the conditions and we pre-compute it. So everything that we would have done serially, we're trying to piece it out and do them one step at a time. Save that data, and then we combining all of those results in a vectorized manner. That's really where the efficiency comes in. So what the isIn would do, it would return 0 or 1 on whether or not something is in a set, right? So what you would do is that you would use the isIn to figure out what is the selection, what are the things that you would need, and then you could do something like this. You could say, okay, this is the selection of the data frame that I want. This is the field. This is the field that I'm interested in, right? And then for those things that are non-zero, we just multiply it by e. Right? So that's one simple way in which you can vectorize. Right, and this is how the code would look. So again, this code science look a little bit more strange than we would, because again, this would have normally been done with a for loop, right? So here's where the efficiency comes in, right? So we use the isIn to make our decisions ahead of time to figure out which row is in what range. And you can either save this onto the data frame directly, or you just save it in a filter here, right? And then we apply the filter, pull out the field that we want, and multiply by the different rates that we want. So you can see here now we go on to 0.008 seconds, right? So we get it even faster. Okay, so that gives us 300 times faster. So yeah, making some progress. All right, so the isIn seems to work fine, but as you might tell, it's kind of clunky, because suppose this is 3, right? But suppose I had 300 ranges or something like that, right? And this obviously is not going to scale. All right, so how would you handle like that? Something like that. Well, there's a thing that's vectorized, what's called cut, right? Which is a sort of a generalization of this. And what that would do is that it would generate the sort of arrays that you would want, right? With the label. So this is a kind of a bin function, right? So we say, okay, these are the bins that I want. I want 0 to 7, 7 to 17, 17 to 24, and so on, right? And then these are the labels that I want to be associated with those bins. So when I apply the cut function, I would get something like this. I will get an array where I would have applied the result, meaning if it was true, we would put it 12, right? So if it was in the first bin, the 0 to 7, we would put it 12. It was the second bin, 7 to 17, we would put 20, and so on. So we get back this array here with all of the values ready to go, and then we could just vectorize the computation, right? So again, here, what you have to understand is that this computation here is happening in parallel across cores where possible, right? And so this is how it would scale easily. Like if you had a Spark cluster and stuff like that, you know, you could get really good efficiency gains. But this is only possible if we did the pre-computation here, right? So the cut allows us to do it in a more generic way, where we specify the bins. Here, the lowest true or false as if you want to include this value in the range. So, you know, less than or less than or equal to like this, right? And then these are the values that you want. So when you apply that there, getting even faster, 0.22 seconds. All right, so that's compared to our original for loop that, you know, I would have been writing. We're talking 1,000 times improvement, right? So yeah, I mean, this is not too bad, right? It's just that I didn't know about these things, and I didn't really understand. I thought I understood how pandas work, but I really didn't. Right? I have a better idea now. So can you get even faster? Well, the answer is yes. And how you do that is you have to dig under the hood. So what you have to understand is that the pandas is built upon the NumPy, right? So everything, because it's built upon the NumPy, especially when you come to deal with array-like operations, almost everything that you can do with an array in pandas, you can do in NumPy, and there's an equivalent, right? Because basically the pandas is a sort of wrapper for all of the NumPy code, right? So for example, we used the cut in the previous example to get some efficiency, but there's a similar type binning function in NumPy called digitize, right? And this is where we start to get a trade-off. And you'll see we get really fast code now, but the code starts to look a little bit more and more strange, right? So it's like a little bit of caveat you have to take. So if you're doing something production, like heavy production, then yeah, you might want to make sure that your algorithm works well first. And then you can spend some time to optimize, especially if it's something that's like the core of your business, right? But at the same time, what you want to do is that you want to make sure that it's maintainable, right? So it's a bit of a trade-off, because, you know, if the guy leaves or for some reason, then who's going to maintain that code base, especially if it's an important system? So it's real interesting, because like you can dig real deep and squeeze so much performance, but then should you, and how do you make these decisions, right? So that might be a whole talk in itself. All right, so anyway, so back to the topic here. So right, so everything that you could do array-wise in pandas, you could do in NumPy. Why the NumPy is faster is because the NumPy just deals with an array. It doesn't manage these sort of generic objects and have to figure out what's what, manage any sort of metadata to make sure that we could you know, maintain our data frames and our series and all of that. So all of that fluff is just cut out, right? And they're nice to have for us because we like to model. But all that is cut out when you go down to the NumPy and you're just dealing with raw numbers, right? Raw array operation. And that's really where the performance gain comes. Right? So how would that look? Well, it's not too strange in this example, probably because it's simplistic, right? Basically, what we're doing is we just create our NumPy array. So please remember, when you're doing these things, you need to make sure if you're using stuff in the NumPy data structures to get the efficiency, you want to mix NumPy with NumPy, right? I'm not sure what would happen if you mix NumPy with pandas. I would assume it would be smart enough to figure out when it could use the underlying NumPy data, right? And so for any pandas series or data frame, if you just say dot values, that returns the underlying NumPy data structure, right? So in this case here, we have our prices array, right? And what this digitized thing would do is that it would, okay, these are the ranges, and for everything in our series, it would assign it to one of these bins. So it would assign it to bin 0, bin 1, or bin 2. So when I call the prices on this here now, this would generate our list with the 12, 20, and 20, right? So before, that list would have been generated simply, so in the previous example, that list would have been generated simply by this call with the cut, right? But then with the, if you're going down under the rabbit hole and you're trying to use the NumPy, then you have to know, okay, this is how the digitize works. It gives you the index references, and then you need to pass that into your array, right? So and the theme is the same. The more you dig under the hood, is the more overhead you have to think about in terms of using that API, but you get the speed, right? So anyway, so basically what this is here is two numpy arrays being vectorized, and that's like, you know, uber fast, right? So we're talking, you know, 0.001 seconds, right? Which is like a whopping 2,000 times faster. Crazy, right? So yeah, so that's pretty awesome, right? So some other things you could do, some other nice stuff is like select. So there's the where function as well, but the where is like to do like one conditional, but you could do multiple conditionals in NumPy using select. So essentially how you would do that is that you put your conditions here, and then the same idea, right? To pre-compute the decisions, right? So this is just a Boolean vector array for each of the different conditions you want. So this is like if the hour was between 0 and 7, we match that to all of the rows that satisfy that. So we would have a true or false array as the length of the data frame, and values that match it would be true, values that match it, right? And then similarly here, this is another conditional, this is another conditional, right? And then these here are the values that should map should these things be satisfied, right? So it's kind of like if that, else, if that, else, if that, and the last case, in the final else, it would just take whatever values here default, right? Okay. So this is how we set that up. And again, you can see the analogy going back to the example that we did before using the NumPy API, which wasn't it was very similar, right? And it's very similar, but this one is a little bit more, right? So yeah, so basically we do that, we get our Boolean values for different conditions, we have our choices, so we just pass it into select. So these are the conditions, these are the choices, this is the value for the default. So this would then return an appropriately filled out NumPy array, which we then vectorize, right? So remember the dot value here is key, right? So vectorize, so NumPy with NumPy, boom, good to go. And we can do this sort of complex if then else, you know, in 0.03 seconds, right? Which is not bad, which is 1,000 times faster than what we had before. Now you could use a similar trick for nested ifs, right? But how you have to do it is that with the nested if. So if I say like, you know, if A is greater than 4, and then inside of that if I had if B is also let me say less than 2, right? What you would have to do is that you would have to put those two conditions here as 1, right? So it's kind of like linearizing the nesting, right? So you sort of flatten it out, you flatten out the nested conditions, and then you put them here as each one of those, and then you put the appropriate values here. So it's a little bit trickier to do with nested ifs, and again, you can see the trade-off here. If you have a very deep nesting, then you know that's a lot of you know that's a lot of flattening you have to do. So you gotta be real careful with your code, and then it becomes a little bit unreadable at that point. It depends on how complicated it is. Because sometimes seeing the nesting, you would be able to understand the logic better. But if you flatten it out, it seems like sort of the language like magic, right? But it is kind of magic because it's moving 1,000 times faster. Right? So yeah, so that's that. All right, so and this was interesting. Just to kind of wrap things up here now. Suppose you wanted to do conditions using multiple rules. So sometimes what you would want to do is that you wouldn't want to make a decision based on the data in one row. You'd want to compare with the row before. So for example, if we was using our data set here and we wanted to work out if there was an increase, right? So this information is indexed on the time, right? So you would have the first time, the time that is the furthest away, that's the first row, and then second, and then third, and so on, in order. So if you wanted to tell that if there was an increase or a decrease, and this is something you would do when you're doing these sort of rolling averages and like the Sarima and Arima and stuff like that. When you do a time series data, this is something you would always have to compare with previous rows. All right, so in this case here, we're just comparing with the row before it, to the I minus 1, with the I, taking that difference and seeing if it's greater than 0. So if it's positive, then that means there was a an increase, and if not, there was a decrease. So you see a similar thing going on here we're doing our enumeration. This is how you normally do it. You have your listing going on and your append and so on. And at the end, now you just parting that list the data frame, right? So again, we back up to 2 seconds, which is kind of slow for 8,000 rows. And again, the issue here is because we have too much non-vectorized statements. So how do we fix that with multiple rows? So admittedly, it is a little bit trickier to vectorize, but again, the idea is the same. You pre-compute the decisions and the actual computations, you vectorize those. All right, so how would you use that? All right, so in this case, the data partners have this thing called shift. I didn't even know that was there. Right. So what you could do is it's like a series, you take a sequence and then you can shift it back one or forward one as the case may be. So basically what we're doing here is we're offsetting by 1, right? So we can get the previous, right? So we shift them back by 1, and then we fill in that with 0, right? So when you fill that with 0 now, the first row, so the first row of the normal data frame would match to the data in this case will be 0 because we didn't have anything before that. But the second row in the normal data frame would match with the first row in the data frame and so on, because we shifted the rows by 1. So what that would allow us to do is that we can now vectorize the computation. So how can we vectorize the computation? Well, simply, now that we have the actual shifts saved as data, we don't need to go look them up, right? So we save that in our data frame, or you save it in our reference here like I have here. And then all you have to do now is just simply compare the current data, right, with the corresponding row in the previous array, and this previous array is shifted by 1. So essentially what we did here is we vectorize the conditions, right? So we do this here now. This would be a vectorized operation. We get a Boolean array that would tell us whether or not this row, this current row, the value is larger than the previous row. All right. And so once we get that there, so in this case, we just want to flag it. So you just have 1 choices, and then you can do this with a where. Might be a little easier with the where, but I just sort of went ahead with the select because it's select a little more general, right? So again, passing the condition choices. So if it matches, we put a 1, and if it doesn't, we put a 0. And yeah, we do this in 0.01 seconds, right? So compared to the normal way, that's about 2,000 times faster. Right, and then this is just the top tip of the iceberg, right? It goes really, really deep. It can even go under the pipe, go under the NumPy hood now if you want, and start to use Cython and stuff. Because everybody NumPy is basically eventually it's a wrapper. It would execute C code, right? So if you're really into that kind of thing, you could even dig under the NumPy hood and start using Cython and just write interfacing with C code directly. All right, so another thing that I didn't know about, right? Oh wait. Oh yeah, so I'm using this thing called Rise, which is really cool. It allows you to present like a notebook in the slide form. I'm not sure if you guys know what I only discovered it for this talk. It's pretty awesome. Right, so you can have like these live things I could actually, so all these things that is code that I could actually run. Anyway, right, so you have HDF source. I didn't know about that. That's a format. Typically, I would just write the CSV or something, or Excel or whatever. But yeah, the HDF store is a format that allows you to load and read and write data frames efficiently from this, right? And it's certainly faster. So this would make a big improvement if you do it with large stores. So it's pretty simple. You just HDF store. You create your managing object there, and then you write it out to this, right? And then you close the object there, and you could also retrieve it. All right. So in conclusion, what I've learned so far is that in general, the pattern for the Pandas API is that the less time it needs to think about things, the faster it can execute. And maybe execute should be replaced with number crunching, because at the end of the day, that is at the heart of all of the algorithms, right? So the concept here is that we pre-compute the decisions. And once we pre-compute the decisions, pandas can then pass it down to NumPy and have it run faster, or you could pass it down to NumPy yourself and have it run even faster, right? So generally, you try to vectorize as much as possible because that is what pandas was built for, right? It wasn't built for for loops or any of these kind of things. It was built to do stuff in parallel, right? If it's really complex to vectorize off the bat, right? You can just reach for the outline, right? Just lambda function it, throw it in there, and you'll get some mean, right? But you should really try to vectorize it. And again, it's not hard, right? Just think about it as memorization. You save your computations in the different stages and the steps as data frames, because once you save it as a column in a data frame and you interact in column to column, you vectorize, right? So there would be performance gain. Even if it's not the most efficient way, it's more efficient than doing it serially, right? So try your best to avoid for loops or loops of in general. Pass them down to the different things in the Pandas API. If possible, all right. I suppose there would be some edge cases where that's really not possible, but as so far from what I've seen, at least in my experience, yeah, I haven't encountered a scenario where you must use a word, right? Again, if you're doing many array-like operations, then in the Pandas API, then you're not really leveraging, you're not really using Pandas. What you really want is NumPy. So if you're just doing a lot of array computations, array number crunching, that kind of thing, then all of the metadata that the Pandas keeps for you to allow you to do the data frame as things is not necessary, and you can just cut that out and map down to the NumPy. All right. But again, with the caveat, depending on what you're doing, because you know, it could the NumPy could look a little strange. So you might want to balance that out. Right. And yeah, in general, vectorization in NumPy is much faster than vectorization in native. Right. So these are some awesome links. Yeah, sure, we did. Yeah. Right. So these are some awesome links that I found. This YouTube video from a PyCon. Yeah, that was really good. Right. So those are the links. Yeah, so I'll post it up in a GitHub link. I'll share it with the group so you guys get access. So that's the end of the presentation there for me and what I've learned so far. And it's really just a tip of the iceberg. So yeah, any questions?